All right, today we're going to be talking about lesson 3.15. This is our last lesson for the year. And all right, let's get started. You guys made it through, 1, 2, and 3. And the quicker we start, the quicker we finish. So, all right, rates of change in polar functions. So, we've seen rates of change. Keep in mind that rate of change is just slope. And so one of the things that we do here with polar functions is we analyze their rate of change. So one of the things that we look at is the distance that's changing with the function and the origin. Is that distance increasing or is it decreasing, right? So let's analyze that. So the distance between the function f of theta and the origin could be increasing, and we see that the r function, or of course f of theta, that's how they'll call this function, if we see that that's positive and increasing, keep in mind what it means when the function is increasing, that means there's a positive rate of change. We could see that f of theta is negative and it's also decreasing, and then that would indicate that the distance between the function and the origin would be increasing. So why does the function and the origin have a distance that's increasing, which just means the function is getting further from the origin, right? So we see a positive number here, right? If we see that f of theta is positive, and when something is increasing, well, that indicates it's got a positive slope. So we know that positive and positive, those make positives, right? And what is increasing after all is just a positive slope, right? So if the function is negative, so that indicates a negative value, and it's decreasing, which is just a negative slope, we know that negative and negative together makes positive as well. So that's how we can conclude that that distance would be increasing. So when is the distance between the function and the origin decreasing? Well, that's when we get positives and negatives together. So if the function is positive but it's decreasing, we'll have that distance actually decreasing. And if the function is negative and increasing, well, then the distance between the function and the origin is decreasing. Okay, so these are kind of like what our scenarios are, and this is how it could occur. All right, this statement below the table here, this is really used for justification purposes. If the polar function f of theta changes from increasing to decreasing, or vice versa on an interval, then that function has a relative extrema. So let's think about that for a minute. If our function is changing from increasing to decreasing, what does that look like? Well, it looks like our function's going upwards because it's an increasing slope, and then downwards like this. So what that means is that that point right there is a relative maximum, right? It's a relative extrema, right? So that's because that function is changing from increasing to decreasing. So we use this in our justifications if we're ever asked where a point is like closest from the origin or even furthest from the origin. Okay, we'll do an example a little bit later, but we're going to be using these words, if you will, in our justification. All right, let's look at the first example here. Given r of theta equals 4 sine of theta on 0 to pi, in other words, here in the graph, we can see that this is the function that's given, okay? Use the table and the graph to complete the following statements. So what we hear is that from previous students that have taken this AP exam is that on the AP test, questions were presented in polar form both graphically, so the graph was given, or numerically, so they may also give you the table, okay? It's either or, it won't necessarily be both, okay? So we should be familiar with how to analyze both pieces of data. So on the interval from 0 to pi over 2, what is r of theta? Okay, so let's look at this for a second. I'm going to look at the table for a moment. From 0 to pi over 2, that's all of this region here. From 0 to pi over 2, all of this right here. Okay, r of theta is what? Well, I'm going to start by looking at the r values. I notice that they're all positive first off. So I'm going to go ahead and say r of theta is positive. And what's going on with those r values? Are they getting larger or are they getting smaller? And I notice that they're getting larger from 0 to pi over 2, which means that those values are in fact increasing. Okay, so therefore, what does that tell me about the distance between r of theta and the origin? Well, this is positive and this is positive, so that indicates that the distance between r of theta and the origin is increasing. right? And where am I getting this? Well, I'm just getting this from our table that we just talked about, right? And these are the two scenarios that could occur, right? So that's what we're covering here. Okay, let's look at the next one. On the interval from pi over 2 to pi. So pi over 2 is over here, and we're going to go all the way to pi this time. So I'm just going to change colors on us. All right, r of theta is blank and blank. All right, well, I notice again that my r values are positive. All right, and the r values this time are in fact getting smaller, which means that these values are decreasing. So what does that tell me about the distance between r of theta and the origin? Well, positives with negatives give me negative, so decreasing. The distance is decreasing. Okay, so at what value of theta from 0 to pi is the polar function furthest from the origin? So from 0 to pi, I notice that the biggest r value here is 4, right? And so I can also, I see that in the table here, but I also see that in the graph. All right, this point is furthest from the origin right there, but we're not asked that it's 4, right? We're asked at what value for theta, and the value of theta here is just pi over 2. All right, so theta is going to equal to pi over 2. If I had to justify this, you notice how these values are increasing, and then all of a sudden they start to go decreasing. And so that has to go with that justification that we just talked about, right? So when the point is farthest or closest to the origin, in this case farthest, right? And we're looking for basically when that changes, when it changes from increasing to decreasing or vice versa, decreasing to increasing, okay? So that's what we can use in our justification. Again, you'll see a question like that coming up here. Here's our next example. Given this function now, from 0 to 2 pi, let's use the table and the graph to complete the following statements. So from pi over 4 to pi over 2, what is r? Okay, I'm going to challenge you guys to pause the video here and see if you can figure out your answers. Okay, so if you were able to come up with your answers, hopefully you figured out that pi over 4 to pi over 2 is this region right here, and those r values are in fact negative, right? So are they getting bigger? Are they getting smaller? What's happening there, right? So it goes from 0 to -2 to -4. Those values are actually decreasing. Okay, and so if the distance, if we have a negative and a negative, then that tells me that the distance from r and the origin is going to be negative and negative. Those make positives, right? So this is actually going to be increasing. Okay. All right, so on the interval from pi over 2 to 3 pi over 4, let's do that in a different color this time. Let's go back to pink. From pi over 2 to 3 pi over 4, so that's all of this now. Oh, I actually was already on pink. All right, so from pi over 2 to 3 pi over 4, there we go. All right, what kind of r values do we have? Well, I notice that they're still negatives, right? But are they getting bigger or smaller? And I notice it goes from -4 to -2. Then all of a sudden we're getting to the positives here. So this indicates that these values are actually increasing, right? So negatives here, increasing is like a positive number, right? And so positive slope, in other words. So the distance between r and the origin is actually going to be decreasing. Again, these are opposites, and so that's what's going to give us a negative at the end. So decreasing distance. Okay, now what if we didn't have the table? What if we only had the graph? Could we answer this? Here's pi over 4, there we go, and here's pi over 2. Okay, if we're following these numbers from pi over 4 to pi over 2, we're probably going this way, and then this way, and then this way, and then this way, and then this way, and you see how they are just getting further and further and further from the origin, right? So what does that tell me? Well, that tells me that the function has a distance that is increasing from the origin, and then that's what we've put over here for this answer, okay? So that's how we can come up with this. Obviously, I think it's definitely harder to do it graphically, definitely easier to do this in a table, okay? Remember, you can always make put your function in the calculator and come up with the table as well. So that's another good strategy. If you're ever just given the graph or maybe given the function this way, you can always come up with your own table. Okay, so what about on the interval from pi over 4 to 3 pi over 4? Well, we already have 3 pi over 4 pi over 4 marked. Here's 3 pi over 4, right? Somewhere over here. All right. Well, what's the furthest distance between the furthest distance from the origin. So the furthest distance that we go from the origin looks like to be this point here, right? Which actually is the length of the pedal, which if we remember should be the amplitude of the function, right? So that should always match up perfectly with that value right there. This should actually be a width of 4. Let's see, 1, 2, 3, 4. Perfect, right? Okay, so the question here is asking, what's the furthest distance between our function and the origin? And that's actually going to be this point right here, which is 4 units out. So you can put r equals 4, you can put something like 4 units, anything like that is going to be cool. All right. You can also look at your table here, and you notice that the biggest number there is 4 units out, right? So again, anything like that, you can even write r equals -4. What we're looking for is basically 4. All right, so let's keep going here. Let's look at a new function this time, and this one's going from 0 to 2 pi. And at what point on the interval from 0 to 2 pi is this polar function closest to the origin? This time we want to give a reason for our answer. So, well, it looks closest to the origin if I'm doing this graphically at this point right here, but I have to give a point. At what point? Remember, these points are always given as coordinates, polar coordinates, r, theta. All right, so in order to do that, I need to come up with the r value where that happens. Well, this looks like an r value of 2, and well, it looks like it's happening here. Okay, how come I can come up with this? So I don't want to just say, oh, that looks like the smallest r value. Well, yeah, it does, but we need a stronger justification if we need to get credit on this. And lucky for us, this is actually going to be an MCQ question, but probably won't say 2 is the smallest r value. The options probably will be something along the lines of the rate of change going from increasing to decreasing. Back to that first paragraph down here that we talked about earlier, right? If the function changes from increasing to decreasing, then that's going to give us the closest or even the furthest point from the origin. So let's use that in our justifications. So at what point is the function closest to the origin? Well, we think it's happening here, right, at 2 comma pi over 2. So let's write that in first, 2 comma pi over 2, and let's write why. We think this is happening because the function, well, what's the name of the function? This is r of theta. So because r of theta changes from, and then what's this function doing? Well, I notice it goes 4, 3, 2. That's decreasing. So it changes from decreasing to then suddenly increasing after this. So I'm going to write changes from decreasing to increasing. Okay, so then what else could I do here? Well, do you think we can define the furthest point from the origin? And we absolutely could. Now graphically, that looks like it's this point out here, right? Well, what about on the table? Well, the biggest number on the table appears to be 6, right? Which corresponds with 3 pi over 2. So I can just say that it's 6 comma 3 pi over 2. And let me write why. This is going to be because r of theta, that's our function, it changes from increasing to decreasing after that, okay? So because r of theta changes from increasing to decreasing. A couple other things that we can do here with these polar functions. Remember average rate of change? Average rate of change is really just slope. In this case, the function that will be given to us in terms of r and theta, all right? So this is like having y2 minus y1 over x2 minus x1. This is slope at the end of the day, all right? We look at slope over an interval, right, from theta 1 value to theta 2 values, and remember that graphically, the average rate of change indicates the rate at which the radius changes per radian in this case. And values of the function can be estimated using the average rate of change r with respect to theta. And that's really just because we're not using x and y here, we're using r and theta. But let's really see what this means, okay? If we had to find the average rate of change of r with respect to theta on the interval from 0 to pi over 6, what are we really doing? Well, we're really going to take our function and we're really just going to plug in pi over 6 minus, then we'll take our function, we'll plug in 0, and then we'll divide this by pi over 6 minus 0. And that's like y2 minus y1 over x2 minus x1. Okay, now these will likely be calculator active, but you know, in the slight chance that they're not, this is still something that we can do pretty easily. Okay, remember that taking pi over 6 and plugging it into your function just means plugging in pi over 6 right there where it says sine of theta, okay? So we want to just plug that in. So let's see, do we remember what sine of pi over 6 is? All right, if you recall from your quadrant 1 of the unit circle, pi over 6 is right here, right? The cosine values are 1/2, then we got radical 2 over 2, and then we got radical 3 over 2, and then our sine value is in fact 1/2 here, okay? So that's not too bad. So if we plug in 1/2 here and we multiply that by 2, half of 2 is just -1, and so we end up with 4 minus 1, and 4 minus 1, let's write that out, is really just going to give us 3. So when we plug in pi over 6, we really just get 3. Okay, I'm going to put a minus, and I actually want to plug in 0 next. And remember, 0 is this coordinate here, which is really just 1, 0 on the unit circle. And the sine value of that is just 0. So sine of 0 is 0, times 2 is still 0. 4 minus 0 is 4. Okay, I'm just plugging these things into the function. And then pi over 6 minus 0 is just pi over 6. I'm going to simplify this a little bit. We get -1 over pi over 6. We'll just do a little keep change flip here. So -1, change that to multiplication. We'll flip this around in case you didn't catch the reciprocal thing here. No big deal. We end up with -6 over pi. That is our average rate of change from 0 to pi over 6. And the follow-up question here is this radius increasing or decreasing over the given interval? And how do we know? So I would say that the radius is decreasing, and I know because that average rate of change is negative. So let's write this out very specific. I'm going to write that the radius is decreasing over, and I want to write the interval. Let's use interval notation this time just to have some fun with it, from 0 to pi over 6. And let's write because the average rate of change, let's abbreviate AROC, the average rate of change is negative. Okay, so that's all we got to do here. And now let's do a more FRQ style question, even though this really shouldn't be an FRQ, but it does give you a little extra practice. Okay, so here in this question, we have a numerical representation here of this function. A couple different ways we can do it, but let's just call this function r, or in other words, f of theta. If we had to describe the behavior of the function from 0 to pi over 2, then that would mean that we're looking at this entire part of the function, from 0 to pi over 2. So let's look at the r values, because when we talk about the function, we're really talking about the r values. Well, what is the function doing? Well, first off, those are all values that are positive, right? So I can say, function has positive values, and maybe I can also say that from 0 to pi over 2, the function is in fact increasing, right? You see all those r values are going up, right? So let's write that. Describe the behavior of the function. Let's write from 0 to pi over 2, so on the interval, from 0 to pi over 2, I'm going to say f of theta is positive and increasing. So just a little extra practice with only a numerical representation, okay? Now let's describe the behavior of the function from pi over 2 to pi, all right? So let's highlight that. From pi over 2 to pi is this part of the graph. All right. Well, the R values are still positive, but this time they're decreasing. So on the interval from pi over 2 to pi, we can say that the function f of theta, and again, you can write f of theta or you can write r. Interchangeable here, doesn't really matter, okay? F of theta is positive still, right? But this time it's decreasing. So it's positive and decreasing. By the way, what does that tell me about the function and the distance to the origin on this interval? Well, that tells me it's basically a positive here and a negative here. That tells me that the function has a distance that's decreasing from the origin. Okay, so keep that in mind. Even though I'm not asking you that here, could be helpful. What's the average rate of change on the interval from pi over 6 to pi over 3? Okay, so this is a really good question. So the average rate of change from pi, let's highlight, from pi over 6 to pi over 3, that's in this region right here. And again, that is really just slope. So we're just going to do y2 minus y1 over, and then we can do x2 minus x1. And I want to put that into the calculator, right? So let's put that in our calculator. By the way, on the bottom here, we're just going to get pi over 6, okay? Okay, so 4.33 minus 2.5. Let's see, we get 1.83, all right? And remember, we want to divide this by pi over 6. Let me write everything out, because if this is an FRQ, we want to make sure to get our credit, right? And so this just means keep, change, flip. But ultimately, I can just do in my calculator 1.83 divided by pi over 6, right? And let's figure that out, right? So let's divide here. Let's put a fraction in place here. And, oops, not x, pi over 6. So pi divided by 6. Alrighty, awesome. Make sure I'm in radians. And when I hit enter, I get 3.495. 3.495. Let's write that out. There we go. Okay, so that is the average rate of change on the interval. Okay, now this next question, estimate the value of pi over 4 in the function. Pi over 4 would fall right here, smack in the middle there, right? So this is something that we do a lot in calculus, right? You guys might remember this from Algebra 1. Y minus y1 equals the slope, right? And then x minus x1, this is called point slope form. Well, in this case, I'm just going to pick an easy point that's on that interval that we just found the slope for, because this is going to be our slope. So between pi over 6 and pi over 3, I definitely like this 2.5 better. So let me use that point right here. I'm going to use that as x1 and y1. Okay, so let's say that this is really going to be y minus 2.5 equals, we got our slope there, 3.495. Now keep in mind that's a rounded value. We might need to use the exact number there. X minus x1, well that's just pi over 6. And if I want to get y by itself, because what I want to do here is I want to plug in pi over 4, but eventually I'll plug in pi over 4. First things first, I want to get y by itself. So the next thing I need to do here is add 2.5 to both sides. So I'll get y equals, all right, we got that 3.495 times x minus pi over 6, right, plus that 2.5 that we added that to both sides. And now, I can take that pi over 4 and plug it in here to this function, okay? We use this a lot in calculus. So, all right, so if I'm going to plug this in, I'm really just going to plug it into that equation I created. Well, 3.495, that's the slope. Hey, I actually already had that in my calculator, except I had the exact number in the calculator, which is even better, you see? So let's take that number and just kind of multiply it by, what are we multiplying by? Let's see here. by x. And what do we want for x? Oh, we want pi over 4. So we're going to do pi over 4 minus pi over 6. We're just plugging that in. So parentheses, and I'm just going to create a fraction here. Pi over 4 minus, and now pi over 6. Oops, I forgot to do the fraction. See if I can do it this way. Pi over 6. All right, let's close up that parentheses there. All right, what comes after that, right? That's pi over 4 minus pi over 6. Next, I need to add 2.5. So let's put that in there. So plus 2.5, and now when you hit enter, 3.415. That should be our answer here. Okay, 3.415. There we go. That is the final answer to this guy. Believe it or not, this thing here, average rate of change, this does come out on FRQ number 2. And on FRQ number 2, I think it's part B, if I'm not mistaken, of that FRQ, they will ask you to kind of do this equation thing and all that fun stuff. And taking that number and using that exact number like what you saw that I did there, instead of using the rounded version of it, could be really important to getting that number there in the last part, to getting that number correct. All right, so we want to be kind of precise. Okay, remember we only round one time, and that's at the very, very end. All right, so that's our last lesson. Shouldn't have been too bad. And I hope you guys enjoyed all my lessons so far. Okay, anyway, you're going to have an assignment to work with this.